is Kraig Winters from Scripps for UCSD.
Good morning. I'm going to talk about the available potential energy, dissipation of kinetic energy, and dissipation of buoyancy variance in a sort of classical problem of steady horizontal convection. My collaborator with this is Bill Young. We're both at Scripps. I'll upload the presentation. If you go to my website now to grab it, you'll find out that my website is being hacked, and so it's under temporary maintenance. I'll fix it when I get back. Thank you very much. Is that better? Okay. This year, Hughes and Griffiths wrote a very nice paper in the annual reviews of fluid mechanics, looking at recent progress on the problem of horizontal convection. And I'm going to present the problem today. It's entirely equivalent as the way that Mike McIntyre introduced the problem on Wednesday morning for us. I'm just going to consider a box of fluid, and I'm going to prescribe temperature boundary conditions on the upper surface such that there's a horizontal gradient in the temperature. And in the configuration that I'm showing there, I've got buoyancy decreasing as I move from left to right. I've just taken a couple of images from the Hughes and Griffiths review paper, flipped them upside down because I did them a little bit differently, just to give you sort of a visual and intuitive feel for the kinds of flows that I'm going to talk about today. So under the influence of these boundary conditions, a circulation is set up, which is generally going to move in a clockwise direction. Cool fluid's going to sink, needs to be replaced by warmer fluid. We get some kind of a circulation. I'm going to be specifically interested in this problem in the limit of steady state. Okay, so I'm going to let this thing equilibrate and drive to a steady state. And I'm also going to be specifically interested in the limit that the diffusion parameters of the fluid are going to zero. So I'm going to take nu and kappa to zero, holding the Prandtl number fixed, just as Michael mentioned the other day. Okay, in their review paper, in the conclusions, they said that an important outstanding problem with respect to this problem, or an important outstanding issue with respect to this problem, was the energetics of this flow, and in particular, the energetics associated with mixing in this flow. On the other hand, Michael gave us a nice explanation that concluded with energetics is not the answer to everything, and a lot of examples in a number of fields of where this is the case. The purpose of my talk today is certainly not to argue with this. I think we can all agree that that's a reasonable statement, but I would like to explore what can a careful energetics analysis of this flow tell us about this flow. So, simple. I'm just going to work with the Boussinesq equations of motion, momentum equation. I'm going to work for a scalar. I'm going to work with the buoyancy B, which I'm going to assume is linearly related to the density rho. So I've got a linear equation of state, Boussinesq equations of motion, and in particular, I'm interested in the limit that kappa goes to zero with Prandtl number fixed, and of course, I'm going to end up in looking at the steady state. So no surprises in terms of the governing equation. It's very simple. This is another schematic that I almost could have skipped, but I just want to introduce a little bit of notation. As I said, the buoyancy is going to be B. I'm going to put this in a box of depth H, and I'm going to specify the buoyancy on the upper surface, Z equals H, and the surface buoyancy is just going to be represented V sub S, a subscript S for surface. That's an arbitrary function of the surface coordinates, but I'm really thinking of distribution where I go from high buoyancy to low buoyancy as I move across the domain. And since I'm free to set the reference point of buoyancy as I like, I'm going to further just specify for notation that I'm going to prescribe the buoyancy on the surface between 0 and some V max. So the surface buoyancy is just going to range from 0. These are the parcels that want to live at the top. 0 buoyancy, which are the parcels that want to fall to the bottom, and to some V max, which are the parcels that want to live at the top. For the record, I just say that the rest of the boundary conditions are constructed to be as simple as possible to focus on the primary issue here. And so I'm going to have free slip walls, a rigid lid. I'm going to look for steady state solutions. And I only point out that in this formulation of the problem, when I specify the buoyancy, the diffusive flux of buoyancy, kappa dB dz, kappa b sub z, is part of the solution, not part of the problem specification. Okay? So as in finding the solution to the problem, one of the key things about the solution is the flux of buoyancy across the upper surface, which jumping ahead, if thinking energetically, we're talking about an exchange of energy from some external reservoir into the mechanical energy of the box. Okay? So simple, but I'll point that out. First thing I want to do, completely trivial, just take the buoyancy equation. It's just an advection diffusion equation under the Boussinesq dynamics. And in the steady state, take a horizontal average. If I do that, what I find out is that I have to have this advective diffusive balance independently satisfied at all vertical levels. So the vertical advection of buoyancy averaged over a horizontal surface has got to be matched by the diffusive flux of buoyancy across that same surface. And this has to hold at all z's. You get this in 1 to 2 lines from this equation. Okay? So this has to hold at all vertical levels z, and in particular it has to hold at the surface z equals h. Okay? At the upper surface z equals h, I know that the vertical velocity has to be 0, so this left-hand term is 0, and so the average diffusive flux across that upper surface has got to be 0. Okay? That doesn't mean that the diffusive flux is 0 point-wise on the surface. That means that in steady state, the average is 0. And I point that out. It seems trivial. It'll come up again later. I point that out that the reason this is going to 0 is because there's a lot of cancellation of positive to negative influences, positive and negative contributions. Okay? So we get this simple result that the average buoyancy flux at the surface, diffusive buoyancy flux at the surface, has to be 0. Okay. I said I was going to talk about energetics, so let's do energetics. Very simple system, box, boundary conditions. Let's formally write energy equation. So let's define a kinetic energy in the usual way and a potential energy in terms of the buoyancy, just an integral z, b, dv. The h is here just to set a reference level, and it's chosen such that potential energy is always going to be a positive definite quantity. Okay, so simple formal definitions of kinetic energy and potential energy. I have momentum equation, continuity equation. I have an advection diffusion equation for buoyancy. So clearly, I can take the time derivative of these quantities and write out energy equations. And this is not new to anybody, obviously, but I'm just going through it to see what pops out. So if I do that, I have a couple of things. So the kinetic energy equation says, first thing I see, let me just go back. First thing I see is I get a transfer between kinetic and potential energy. I have this same buoyancy flux term with opposite sign. So kinetic energy, we lose kinetic energy as it's converted to potential energy and vice versa. There's a negative definite dissipation term, so kinetic energy is dissipating. And I have this term here, which is sort of the analog to this, but not exactly. There's a kappa, so it clearly came from the kappa grad squared b term. But this is the term that you get from, to get the potential energy equation, you have to multiply the buoyancy equation by z. So now you've got a z kappa grad squared, and you can distribute the divergence operator and convert a volume to a surface integral, and you get this term here, which is a surface integral with kappa in front of it. Note, though, this is b z dot n, which is only, z dot n is a normal vector pointing up from the upper surface and down from the lower surface. But this is not the buoyancy flux, this is the buoyancy itself. And from an energetic point of view, this is a transfer of energy between internal and mechanical energy. Okay? This is not a statement of the energetics associated with a diffusive buoyancy flux, but this is a transfer between internal and mechanical energy. Okay, so if I take those two energy equations, simple energy equations, and go to steady state, the kinetic energy equation just says these brackets are just volume averages. In a volume average sense, the kinetic energy dissipation is balanced by the buoyancy flux, dissipation defined such. And from the potential energy equation, I find out that the buoyancy flux is balanced by this exchange with internal energy. And this is the difference between the average buoyancy on the upper surface, which I prescribe, and the average buoyancy on the lower surface, which I don't prescribe. On the other hand, in steady state, I have a maximum principle, so I know something about the limits, the constraints on the limits of the buoyancy on the lower side. Now, the potential and the kinetic energy equation simply reduce to these two balances, both of which involve the buoyancy flux. And if I was to be so bold as to note that I could then set these two things equal to one another, I might generate some rather heated discussion on this, because this is basically the Paparella-Young anti-turbulence theorem, which says that in steady state, the fluid is, quote, non-turbulent in the sense that epsilon goes to 0 as kappa goes to 0. I'm not being saved by any gradients at all. This is bounded quantity, and as kappa goes to 0, epsilon must go to 0. Okay, I don't want to talk the semantics of that. We'll get to it in a minute. But so that's what comes out of a basic energy analysis. And so from that equality, since I have a maximum principle and I'm specifying the maximum buoyancy at the upper surface, I know that the dissipation has to be bounded by that quantity. And if I go and consider this as a very idealized model of large-scale ocean meridional overturning circulation, then I can put order of magnitude estimates on the various terms, and I find out that epsilon has got to be less than something like 10 to the minus 13 watts per kilogram. Now, the observed dissipation in the ocean is on the order of 10 to the minus 9 watts per kilogram, and this is what Michael was talking about yesterday when he said the limits is 3 orders of magnitude too small. Clearly, there must be other mechanical sources of energy, winds and tides and possibly fish, that is stirring the ocean, giving us the dissipation rates that we see. It is not possible under this simple configuration to drive a circulation that can dissipate anywhere near as intensely as the ocean that we observe. Another simple way of thinking about it is that, in other words, if I demanded that I match the observed value with epsilon and I chose the value of B that I would need to get that, I'd have to boil away the ocean in order to do it. So it's not going to happen. Okay, so from the simple mechanical energy balance, I gave you the equations. I just want to show it to you schematically. Everything's in steady state. Potential energy is being converted to kinetic energy at a rate given by the buoyancy flux, which is matched by the dissipation of kinetic energy, which is a transfer to internal energy at rate epsilon. Those have to match. And internal energy is actually supplying potential energy to the system at this rate. This match here is the Paparella-Young theorem, and this is just an equivalent thing. So all these arrows are equal. We have a bound, okay, and the energy transfers around this little circulation are feeble in compared to the energy transfers that we're seeing in the real ocean. Okay. So, a couple of things just from this little section. The observed level of real ocean dissipation requires additional sources of energy. We've seen that. This is provided solely for your entertainment and amusement. It's either semantic or philosophical, depending on your point of view. But I tried to restate the anti-turbulence theorem simply by pointing out that the idealized buoyancy force ocean is not 3D turbulent in the sense that the dissipation rate vanishes as kappa goes to 0 rather than approaching a constant which is independent of the variables. And I've added the 3D to distinguish from 2D turbulence, which is non-dissipating. Anyways. But the real point here is that in everything that I've done so far, nothing explicitly ever appeared about the transfer of energy from the external world to the ocean or to the circulating flow. That did not appear, okay? Also, I never saw anything about the energetics of mixing. Mixing and the energetics associated with it never appeared in those equations. And that's a little bit disturbing because one might think that those are fairly important pieces of this problem. Okay, so before I get directly to the energetics of mixing, let's take a little bit of a sidetrack and we'll look at the dissipation of buoyancy variance chi, which is clearly related to mixing, but it's not in terms of energy, and so we'll have to back up a little bit. But let's look at chi, which is the diffusive rate of destruction of buoyancy variance, and define it in a volume average sense like this. It's a basic measure of diabatic mixing and water mass transformation, and it will have something to do with the mixing that we're interested in. I can clearly write an equation for the buoyancy variance, and I get a time-dependent term and two terms over here. I'm going to have let's see, what do I do? Okay. Let's just go straight to the steady state limit. So that term's gone. So now I've got a two-term balance between the dissipation of buoyancy variance chi and its production. And its production is happening at the surface, z equals h, and the rate at which buoyancy variance is being produced is determined by this correlation between the buoyancy itself, which is specified, and the buoyancy flux, which is unknown or part of the solution. So how those two things correlate is going to tell us is the rate of supply of buoyancy variance, which is going to be balanced by its rate of destruction. Okay, so what I would like to know is, in the limit that kappa goes to 0, how does chi behave? So I'm going to use this expression for chi to think about that. And at first glance, you might say chi goes to 0. It's pre-multiplied by kappa. As kappa goes to 0, chi goes to 0. But that's, we can't go that fast, because it's possible that b sub z could get very large as kappa goes to 0. Asking how does chi behave in this limit is essentially asking what is the thickness of this thermal boundary layer in the limit that kappa goes to 0. And it's quite possible that this could get so thin that chi could be arbitrarily large or approach a constant or whatever. So that's my first question, is how does chi, we've seen how epsilon behaves and it vanishes as kappa goes to 0, but it's not for sure that chi will also vanish as kappa goes to 0. And I just remarked that this is equivalent to asking what's the boundary layer thickness as kappa goes to 0. Now, in our paper, we have a rigorous proof that chi is going to go to 0. And out of that proof, you can extract a boundary layer thickness. And I'm not going to go through that here. You can see it in the paper if you like. I'm going to give sort of a hand-waving scaling argument that produces the same boundary layer thickness, and then move on from there. Okay, so we could ask ourselves, what's a thin boundary layer up at the upper surface? Let's write a boundary layer thickness delta, which might be nu over some u, where u is the velocity jump over this boundary layer, which I don't know at this point. If that were to be the case, the average dissipation within that boundary layer would be nu times du dz squared, so it would be this quantity. If I then assumed that all the dissipation in the box were to occur in that thin boundary layer, I could then ask what would be the average dissipation in the box, which would just be a geometrical reduction of the average dissipation in the layer, and I'd get an expression like this. On the other hand, I already know that I have a limit on epsilon, and I know that epsilon's got to be feeble. So I can combine these two things together to pull out both the velocity jump and the boundary layer thickness, and the boundary layer thickness turns out to be kappa to the 2/3, which is much thicker than order kappa, and that's what allows me to say that chi is actually going to 0 in the limit that kappa is going to 0. Okay, so using the scaling estimate, just putting it back into the chi expression, I get an expression for chi, and it goes like kappa to the 1/3. Okay, this is fine, this is great, this is telling me something about mixing, this is telling me something about irreversible diffusion, but I'm not working in units of energy per unit time, and this is a little disturbing. I want to get back to the energetics part of this problem. Yep, we did this. Okay, so we learned something about chi, but we're unsure about its relationship to energetics, and I still haven't explicitly seen the energetics of the surface buoyancy flux coming into this problem, or the relationship with the external supply, which I guess is the same thing. Okay, so to proceed, you'd have to take the potential energy that we talked about and split it apart into available potential energy and background potential energy in order to see what's going on with the mixing. And you can do this formally. I'm going to pretend that I'm a parcel in this fluid and I have some buoyancy B. What I'd like to know is, where do I live after we adiabatically restratify this fluid and put all the heavy parcels at the bottom and the lighter parcels at the top? If I'm a parcel, where do I live in that distribution? Well, I can write the answer to that formally quite simply. If I'm a parcel with buoyancy B, I'm simply going to scan the rest of the volume, and I'm going to look for all parcels that have less buoyancy than I have, and each time I encounter such a parcel, I'm going to get a 1 out of this step function. Every time I don't, I get a 0. So I pick up a 1 every time I find such a parcel. And so I pick up a little differential unit of height, dv over a, or a dz star. So I build up the height simply by this. The details are not important, but since I can know the height, the reference, basically this gives me a recipe for finding the reference profile, I can formally identify the potential energy associated with this reference profile, and I can formally differentiate with respect to time and derive an evolution equation for it. Clearly, this is just some function of buoyancy, and buoyancy obeys an advection diffusion equation, so I can walk through all this stuff. So if I know the background potential energy, I already have a definition and an evolution equation for the potential energy. If I do it for background potential energy, by default, that also gives me the available potential energy because it's just the difference of the two. So if I take the potential energy, split it into available and background parts, and go through an energetics analysis just like I did on the total potential energy, I get two equations. Okay. The couple of terms, let's just go through these. If you're familiar at all with the 95 energetics paper with Jim et al., my notation is such I call this term phi sub d. This is a term that describes the energetic consequences of diffusion of buoyancy variance against the reference stratification profile. Okay, so this is the energetics associated with irreversible mixing in the volume. I see that this is always a source of background potential energy, in the same term with a minus sign, a sink in available potential energy. All that's saying, as a fluid parcel tries to advect back towards its equilibrium position, it diffuses as it does so. That produces background potential energy and loses some of the available potential energy. Okay? Got a next term of interest. Finally, I'm getting something where the diffusive buoyancy flux at the surface explicitly appears as a source term for an energy equation. So now I've got that, and you notice again, it's a source term in the background potential energy and a term of opposite sign in the available potential energy. This is the familiar buoyancy flux term. This is that exchange with internal energy we saw before, and notice it's not a derivative, but just the buoyancy itself. If I take this to steady state, then clearly the time derivatives go away, but a few other terms go away. This term goes away because we already saw that the average buoyancy flux over the upper surface is 0, not pointwise, but the average is 0, so those terms go away. So in steady state, the background potential energy equation ends up as a two-term balance between production of background potential energy through the surface buoyancy flux at the surface, which again looks just like the production term for chi, almost. It's a correlation between the diffusive flux and some other order 1 quantity at the surface. Z star has got to be between 0 and h. And so anyways, this is very analogous to the term for chi, but it's expressed specifically in terms of energy now, which we can see. So I get this two-term balance in available potential energy, and there's 4 terms, and I'm sort of going to consider them 3 terms I just want to take these 2 middle terms together, and so the available potential energy has 1, these 2 together, and then 3. Now, schematically, this looks like this. Everything's got to be in steady state, so now I've got a little picture from these equations where I have the external energy, the internal energy, and the mechanical energy in our flow system, which is divided into available background potential energy and kinetic energy. If we remember what the available potential energy balance was, shown schematically, it's like this. And available potential energy is converted to kinetic energy through the buoyancy flux. These 2 terms that I took together represent an exchange with the background potential energy, and the source of available potential energy is this diffusive flux and comes from the external energy reservoir. The kinetic energy equation that we saw in the beginning of the talk was a 2-term balance between production by buoyancy flux and dissipation by epsilon. If I were to take these potential energies together, our potential energy equation originally was putting the rest of the arrows on, I get this. So thank you. So what I see is that an energetics analysis of this flow simply decomposes into two, I have, and I'm not sure it's the best, I've called them independent, but two separate closed energy cycles involving the mechanical energy of the system and the internal and external energy reservoirs. Using our scale estimate for delta, we can get a bound on the transfer rate associated with these white arrows, which are all equal, and it goes like kappa to the 1/3 in the limit that kappa goes to 0. So this energy cycle is also vanishing as kappa goes to 0, and we already saw earlier that this yellow cycle is particularly feeble. So just to conclude, in steady horizontal convection, if we stick with the Boussinesq statement of the dynamics with a linear equation of state, an energetics analysis, of course, can't tell you everything, but it can tell you something. And when you break it apart carefully, it gives you an energy budget which consists of two closed cycles linking the internal and the external energies with the mechanical energy of the system. We have formal bounds on the energy transfer rates on both cycles, and that all of these energy transfer rates vanish in the limit that kappa goes to 0. Okay? And a conclusion that we already saw from just part of this is that buoyancy forcing alone is insufficient to drive a meridional overturning circulation with the observed dissipation rates. Now, in 1 minute, do I have 1 minute? 1 minute. A natural question is, okay, you've taken the situation where the buoyancy is specified at the surface. What if you had taken it with the buoyancy flux specified at the surface? So suppose I had taken the buoyancy flux B to be fixed in the limit that I took kappa goes to 0. I can still get the same boundary layer scale, but now I can't regard B max as a specified quantity, so I'm not quite sure how B max behaves as kappa goes to 0. But I can, what am I trying to say? If the flux is kappa times B sub z, and I introduce this boundary layer scale here for the scale in this expression, then this has got to be independent of kappa as kappa goes to 0. This goes to B, which is independent of kappa as kappa goes to 0. And you find out that now B max, which is now part of the solution instead of part of the separation, B max must go to infinity as kappa goes to 0, but it goes to infinity very slowly, only as kappa to the minus 1/4. And Paparel and Young result still holds, only in Paparel and Young, this holds regardless of what boundary conditions I choose. This is a limit if I regard that as fixed, and the only point is epsilon still goes to 0, but it goes to 0 just slightly slower when I switch to flux boundary conditions as opposed to fixed boundary conditions. Thank you.
Yes, Michael.
That was really nice, clear exposition, Craig. I would make one point, that is when you go to the nonlinear equation of state, then it's no longer a matter of energetics only. There are functionals coming into the extended proof that are not energetics functionals. And a way to remember that is actually the result depends on the concavity of the temperature nonlinearity. If it happened to be the other way, we can't prove the extended theorem. And that is weird, but that's what happens. There's nothing to do with energetics, that part.
Other questions? Sorry, you were going to respond.
Well,
Yeah.
There's nothing new in energetics. Energetics says this, it doesn't say that, it might say this. There's been a lot of discussion about what is and isn't possible in the system, even under these simple dynamics. And this is simply an attempt to ask, what does the energetics tell us? And I submit that it has told us some things different than some of the hand-waving arguments that have been proposed.
I absolutely agree. Energetics is part of the story. Only mistake is to think it's the whole thing.
All right. Agree completely.
Good.
It's, we know better than almost anything else in the ocean what the surface buoyancy flux is. So why don't you bring that into the argument rather than restricting so completely to use of sort of laboratory analogs. And, you know, in particular, for a unit of surface buoyancy flux, you get more APE creation in proportion to the layer depth, which is upper mixed layer depth, which is filling with convection.
Well, I mean, the short answer is that if you take, I mean, I'm not saying this is the better approach or anything, but if you take the approach that we took, you can derive some results, you have faith in those results, then you can go back and ask yourself, how does the system behave if I had imposed flux instead of buoyancy, and show the small modification to the results, which are essentially that epsilon is still vanishing.
Well, isn't it true that in both of these cases you've used in the limit of kappa going to zero, you're squelching down the system with essentially zero surface input of potential energy, and it seems to me that that's something we can measure and see very clearly in the oceans. And we don't have a simple boundary condition on the top of the ocean. We have a two-fluid interaction with the atmosphere, and it creates substantial heat flux and substantial potential energy creation.
Okay, so I clearly didn't explain this last slide very well, but if I take the limit with where the buoyancy flux across the surface, now I can specify it as a function and a function of horizontal position. I want to keep the buoyancy flux finite, but take the limit that kappa goes to zero.
So you get big temperature differences.
Right. Excuse me?
So you get big temperature differences in your model.
Right. You get big temperature differences, but go kappa to the minus 1/4. They get large very slowly with kappa, and that's not a fast enough singularity to change the essential nature of the problem. I guess that's the argument.
Perhaps we should stay approximately on schedule.
Okay.
Continue the discussion afterwards. Coffee break.